All right, I'm going to end up posting this PowerPoint on the website on Schoology, but this has a lot of animations in it, and I think the more and more different versions of Microsoft Office that people work with, the less and less they work. So I usually end up playing for them for everybody in class, but this time I'm going to end up doing it on screen. You should have seen this happen in the Waves on a String app when you interact two separate waves. This is called the principal superposition. Basically, the way it works is this. Unlike matter, waves can occupy the same space at the same time. So when they are right on top of each other, which is what superposition is, what you see is that they end up adding up. You see two separate waves here, they add up to one big wave. The resulting wave that you would see, the resulting medium that you would see is the blue. And it's composed of basically two individual waves. You see this happen at the ocean a lot when you look at one wave going backwards and the other wave going forwards, and then once they hit, you get a big wave. And then if you notice here, what ends up happening is they actually pass through each other as if they didn't interact at all. So you get their amplitudes adding up here, and that's because both amplitudes are positive in this case. It is possible to have amplitudes that are on the opposite side of the medium, and you should have seen this in the Waves on a String app. And what ends up happening is that if you pay attention to this one really closely, you watch the two peaks, they're matched in amplitude. There's a specific point in time where it was very short-lived, but you get the superposition actually having the two waves cancel each other out temporarily, because what ends up happening is that they pass through each other as if they didn't interact again. So waves can add up, but waves can also cancel each other out, and it all depends upon whether their amplitudes are positive or negative. We also saw on the app that you get wave reflections. Every time the medium ends, that's called the boundary, and the boundary is going to cause a reflection. This wave gets reflected from right to left. The motion of the wave completely reverses. It actually causes the wave to be inverted on the other side of the medium, unless it's a free end, as we saw in the app. But what we really want to focus on is the idea of the standing wave apparatus. Basically, what ended up happening was we're sending waves this way with our string vibrator. They reflect off this boundary, they come back here, they reflect off here, then come back here. You get a bunch of waves just reflecting back and forth and back and forth. And depending upon the oscillation that we had with our string vibrator, you may have seen one of these patterns in that lab that we did. Now, what's actually happening is you're dealing with two sets of waves, one coming from the right, one coming from the left. And if their frequency is just right, what ends up happening is that they interact with each other so perfectly that you get this happening. Now, this is actually like a slow-mo view of the wave here. Basically, if you look at this figure, this is probably a lot better at describing what ends up happening. If you take a look at the blue, those waves are moving to the right, and it's a continuous wave that happens over and over again. The reflections come from the left, and they're always going to interact with each other in superposition, and what you get is just one medium, which is in black here, which is displayed. That's what you can see with your eyes, is the black medium. And this is what the standing wave looks like in slow motion. It's got a few characteristic points of it. Take a look at the red dots there. Those points, their amplitude always ends up being zero. Anytime the red and blue waves interact, they cancel each other out at that point there. It's always zero. Now, this wave oscillates between maximum positive amplitude and maximum negative amplitude, and this point over here does as well. These are called the antinodes, and the red dots are called the nodes. So the points where you have maximum amplitude are the antinodes, and the points where you have an amplitude of zero all the time are called your nodes. And what ends up happening is that there's a lot of different possibilities here. We went far beyond this. This is called the fundamental wave, or the first harmonic right here. This is called the second harmonic. You may notice, look, we have two nodes here, one antinode. We have three nodes here, two antinodes. Take a look at third harmonic here, always gaining a node and an antinode each time. And, you know, you get this very blurry view of the standing wave. That's what we saw with our eyes, and that's how we identify nodes and antinodes. One of the things that we want to recognize, though, is that if we could look at this, the string in slow-mo, you're not going to see this. You're going to see individual snapshots of the medium itself. And what ends up happening is that if you were looking at our string in slow motion, it would look like this for first harmonic, second, third, fourth, and fifth. However, because our eyes can only resolve so much, you end up seeing that with your eyes when these standing waves are formed here. But there's no limit to how many harmonics we can have. You may notice that first harmonic has 2 nodes, so second harmonic has 3 nodes, and you always have one more node than your harmonic number. And what we're going to do is take a look at the formulas here for both wavelength and frequency of your standing wave. So let me diagram them out really quickly and then just describe to you what that means, or what all the variables mean. So if you think about the patterns that we saw, I typically like to refer to them as loops because it kind of makes sense. It looks kind of like a loop. But here's our string, and it's got 2 ends to it. The length of that string is L, right? Capital L. And when we vibrate it, the first harmonic, that's a pretty crappy picture. Let me actually get it to the length of L. Looks like that. And it's very blurry. Here's your 2 nodes. There's your antinode. Harmonic number. The symbol that we're going to use is N. It's harmonic number 1 right there. If we want to look at the second harmonic, the length of the string is still the same, and it will be. But now we got 2 loops here, and you got 1, 2, 3 nodes. Harmonic number 2. Third harmonic will look like this. Again, you kind of get that blurry view. 1 node, 2 nodes, 3 nodes, 4 nodes. There's your third harmonic. And probably the last one I'm going to draw is the fourth harmonic here. 4 loops. So harmonic number corresponds to number of loops perfectly for us. And what you should have noticed is the pattern's very easily identifiable. For example, if this happened to be 5 Hertz based on the experimental setup you've had, second harmonic would be 10 Hertz. This would be 15 Hertz, this would be 20 Hertz. That's not a coincidence. Your higher order harmonics are always a multiple of your fundamental frequency or your first harmonic here. And one of the things that we want to look at is the formula for wavelength. The symbol for wavelength is lambda. And sometimes I'll put a subscript of n there to tell you that each of these waves has a different wavelength to it. And you can always calculate the wavelength. What it is 2L over the harmonic number. Here's why. If you think about the snapshots of the wave, we can look at one snapshot or we can look at the others. Let's actually focus on the second harmonic right now. Look at the medium itself. It either looks like a positive sine wave or a negative sine wave. And I'm going to draw one little snapshot of the wave right here. There's that full oscillation. That's one full sine wave. We have one full wavelength here. So the wavelength, if I were calculating this, it would be 2L over harmonic number 2, or I would expect the wavelength to be L. And I draw a single sine curve, and that's what one wavelength is. I would draw a single sine curve there and see that my wavelength is smaller. What would it be? Well, it would be 2L over 3, or 2/3 the length of the string. 2 loops is always a single wavelength. So let's take a look here. Looks to me like exactly half the length of the string. And when we look at it, it'd be 2L over 4, which is 1/2 the length of the string, or 1/2 L. Now up to this one, there's a reason I skip over this one first. You only have 1 loop there. That's only half the wavelength. The other half would have to be all the way out here. If you look at the wavelength for first harmonic here, it would be 2L over 1, or 2 times the length of the string. So you can't even see a full oscillation for the fundamental frequency. but each other's, you can always lock in on the wavelength by measuring 2 loops. That's actually why in the lab I measured 2 loops each time when we were looking to get the wavelength here. Now let's just say, for the sake of argument, that this L happens to be, let's say, 1.5 meters, something close to what we had in the experimental setup. If we were calculating the frequency, excuse me, not the frequency, the wave speed, this equation that we saw from last week, velocity equals frequency times wavelength, that holds true for every wave. And what I can do is I can multiply the frequency times the wavelength here. This would end up being 2 times L. If L is 1.5, this would be 3. So if you were looking at the velocity of the wave here, it would be 5 hertz times 3. I would get 15 meters per second. That's how fast the waves go back and forth along the string when you send them through. And when we up the frequency, let's make it 10 hertz. If you look at the wavelength here, it is equal to, that's supposed to say L, just the length of the string, so 1.5. And what you're going to get is that the wave speed is still the same along the string, even though we up the frequency of it. It's actually the tension in the string that's going to determine how much speed it is, not the rate at which we oscillate the string. So if you look at the next one, you have 15 hertz, and this is 2/3 the length of the string. So what would that be? 2/3 times 1.5. It's exactly 1, right? And then if you look here, we get 15 meters per second again. If you do 20 times whatever this wavelength is, it would be 20 times 0.75 actually, and you're going to get 15 meters per second again. So the wavelength, the speed along the string is constant in all your setups as long as you don't happen to change anything. If we're working with a different length of string, we might get a different wave speed. So it is possible, in fact, in your lab, you should get different wave speeds, as I ended up tweaking the experiments ever so slightly. Hopefully this is going to help you get through a lot of those wave questions that you may have been wondering about. So last thing I'll just do is we actually have a formula that relates frequency based off of these two as well. So the 3 formulas for standing waves that we really need to know are that the wavelength is equal to 2L over the harmonic number, and then frequency, it actually can be calculated like this: NV over 2L, where V is the wave speed and L is the length of the string. And then last but not least, this would also apply. So those are like the 3 golden formulas for standing waves.